Yeah, so as mentioned, I'm going to be talking about a centralized machine learning system. Can I get a show of hands just very quickly? Has anyone here been exposed to Spark before? Okay, awesome. And has anyone done any machine learning with Spark or with some other system? A couple? All right, awesome. So I'm going to talk you through a journey that I went through with one of the communications company in Australia, where we tried to basically build a centralized machine learning system. So before I get into that, I'll just quickly introduce myself a little bit. So as mentioned, I'm a principal machine learning engineer at Simple Machines. Simple Machines are a consultancy based out of Australia, and we basically do data products and data platforms, ranging from kind of data streaming and big data through to machine learning and analytics systems. So before we actually get into some of the details, I just want to run you through some of the ways that you can actually set up these organizational structures for data science and machine learning. So you can imagine on the sort of far left-hand side here, you can have this sort of very centralized capability. And what this is you have a centralized team where the various projects that want to get some machine learning insights will give that to this centralized team. They'll do the work and then pass it back to the different projects. Then you can kind of move through to a less centralized one, which is still primarily centralized, but you have data scientists working in the various projects and then doing most of the work centrally. Then you can move across to this kind of mostly distributed approach. And the idea here is that you have each one of your teams focusing on solving some business problem, but you're sharing the kind of common bits and pieces that are true across all of your data science projects. And then finally, you can have this complete data silos approach, which is where every single team is independent and ultimately doesn't really share anything. So as you can probably imagine, the two main approaches that people want to end up at is one of these two middle ones. And specifically, the telco that I'm speaking about today, they were aiming to end up with the mostly distributed data science capability so they could focus on actually delivering business value in the various teams. But they could still share some of the common stuff. And in order to share that stuff, they wanted to have the data engineering team actually working on building out the sort of common infrastructure and the pain points of scaling the big data solutions. So if you consider the data science workflow sort of from a million miles away and squint a little bit, it might look something like this. So you start with a business problem. You want to do some kind of data extraction and data exploration. And then from that, you'll start to look and build some features. And then the features will go into a model, which you'll use to train and try and predict whatever the thing that you're trying to predict is. And then you'll evaluate that output, see how good your predictions are. And there might be a bit of a cycle kind of going back and forth with this features and building of models. And sometimes it goes even further back. And then finally, once you're happy, you want to put this into production. So you want to serve your model and make predictions. Now, the entire process often ends up looking something more like this, but we'll skim over that for now. So there are three kind of key points, and that is data extraction, building of features, and model serving that require a lot of data engineering skills. And as I said, the data scientists should be focusing on solving business problems where possible, rather than trying to build and optimize this code and make it run on distributed systems and so on. That's the purpose of data engineering. So I'm going to focus, initially there's the ETL idea, the data extraction and so on. I'm not going to spend any time on this today. It's a lot more complex than it sounds like it should be at scale. But what I'm going to spend a lot of time on is feature engineering. And feature engineering, I'll explain the process of what that actually means and why it's a tricky thing and an important thing to scale. So first of all, just taking a step back, what is machine learning at all? You probably think things along the lines of Terminator or maybe self-driving cars or AlphaGo, some of the really cool stuff that's happening. But the reality of machine learning for most enterprises is actually that they're doing this kind of stuff. So in this example, it's called clustering. Basically, we've got two groups of customers, and we want to classify them as either a luxury segment or knitting enthusiast segment, for example. And what this is doing is basically just finding whether or not to put them in the red group or the blue group. And you can see here the axes are actually labeled with question marks, and we'll see why that is in a second. So another example might be a classification problem, like whether or not someone's going to churn. So you can see here we've got examples of whether or not a user is churned, marked in red and blue respectively. And again, we're drawing a line to separate these two things. And we've got these two axes with question marks. So what are the question marks? Well, ultimately, these things are actually our features. Now, the idea here is that since we can't directly measure churn, we need to instead try and predict churn using something we can measure. And these measurements are actually called features and are typically associated with an entity and an instance in time. And it can be as simple as just raw data coming out of some system somewhere, or it could be a complex transformation of some sort. For example, with windowing, you might think, how many times has my user clicked on this particular web page in the last 30 days, for example? That would be considered a feature for a customer at a particular point in time. And the reason that these are really important is because the majority of machine learning performance actually comes out of features. If we take a look through how this actually runs in practice, what typically happens is you've got a bunch of data sources, you have some kind of feature engineering, and this feature engineering ultimately will spit out some data about a particular customer, for example, at a particular point in time. And then we want to attribute this to a label, and a label is the thing we're trying to predict. So in this case, it would be whether or not a customer has churned or not, given this set of features. So the point of a model is that we train these models and we try and learn a relationship between these features and the actual label that we're trying to predict. So here you can see we've learnt that the red feature when it's greater than 30, and say the yellow feature when it's equal to 7, when it's not equal to 7 is going to predict churn, as an example. And we can see what this looks like when we actually get some data at scoring time. So what happens is we get in an example, say we want to see if Jason is going to churn, and it'll be, they'll have a blue feature value of 12, a yellow feature value of 3, and a red feature value of 33. And so at the first step in this decision tree, we'll see that it is greater than 30, so we'll go down to the right. And then we'll see that the yellow feature is not equal to 7, so it will go to the left, and we'll end up predicting that Jason is going to churn. Now, this is obviously a very, very simple model, but conceptually, all of them actually more or less work in the same kind of way. Now, there are two main sort of usages of features, and this is in training and at scoring time. And the training data set will typically be very large. It'll use lots of historical data, and it will use a lot more features than you end up using at scoring time. Now, scoring, on the other hand, is where you make predictions. And this typically uses a subset of the training features, and it's only usually calculated for the most recent data. So you don't need to worry about what Jason did for the last 20 years. You only need to know what his current state is so that we can predict whether or not he's going to churn. Now, with this entire process, we basically have something like this. We have the feature logic that creates our table. We have some iterative training process, and very often the models will actually learn, or you can do things like feature selection, where we actually cut down the set of features that end up going into that final model. And then we want to take this feature logic and we want to take that final model and put it into production. These are the kind of two key parts of productionizing the machine learning systems. And so what a lot of companies tend to do is they'll spend a lot of time working on various projects and trying to do some machine learning without actually investing a whole bunch in infrastructure. And then they'll get to a point where they realize they're doing a lot of the same stuff. And so they come up with this idea of a feature store. And so a feature store is basically a data store that holds features for some given scope of the business. And this could be, say, a customer or a household. And it's typically at some time granularity. So very often you capture them as a particular timestamp, and then you might roll them up to, say, daily, weekly, or yearly. So there are a few different ways that you can represent these kind of feature stores, but two of the very common ones are using EAVT and tabular. So EAVT stands for Entity Attribute Value Timestamp. And what this looks like is this. Each one of those things is a column, so the entity might be the customer, the attribute might be the actual feature type, the value is obviously the value of that particular feature for that particular entity at the given time, which is the final column. So you can imagine this is fairly efficient storage, especially when you start thinking about adding features, because it's just adding new rows to this table. One thing to note is that the value column doesn't actually have a consistent type, so you have to keep that mapping somewhere else. But the one major issue, at least naively on HDFS and the kinds of things you use with Spark, is that it's really inefficient to turn this into the format that you need to do training on. So we saw that what we're effectively trying to do when we're training our models is to find a relationship between the blue, yellow, and red feature and the actual value of whether or not someone's going to churn. Now, the other approach is tabular, and this looks something more like this, which is basically what our pivoted table ended up looking like. And so you can imagine that this, for machine learning use cases, is dead simple. It's incredibly efficient because it's already in the format it needs to be in. But you've got this extra complexity of adding new features, which is that you actually have to do some kind of join to get them into the same table. And this obviously can become quite expensive as well. So just for a bit of context, this telco had an on-premise data center, and they were often fighting for cluster resources. So we were also using some of the older Spark versions at the time. And we ended up doing a few quick experiments with the EAVT and the tabular format, and with the given resources and so on, actually found the tabular format to be slightly more efficient. But this is very much an implementation detail. And this will probably change over time and will very likely be different for different technology stacks. But what we did is we took a step back and said, okay, if we're going to build this centralized feature store, what do we need? And the first thing that you need is an idea of what a feature actually is, what the feature definition is. And so we came up with this idea of a feature library. And the idea here is that it's a single source for feature logic. It will be loosely coupled from the various systems that actually want to use it, and it's source controlled. And this particular company was using Spark extensively, and so we said, okay, they're quite familiar with this, let's see what we can use in the Spark libraries to actually implement this stuff. And so we came across these things called transformers. And what transformers are is they're basically a transformation that lets you take in a data frame and spit out a new data frame. And you can spit out pretty much an arbitrary new data frame if you really want. All you need to do is define the output schema. So what a lot of the machine learning libraries built into Spark do is they basically spit out a new column with the transformed data. So you have the old version and the new version. And so what we did is we built a very simple wrapper on top of this. The users were mostly familiar with the Python and the sort of object-oriented concepts. So all we did was make this sort of wrapper that enforced that they provided us some properties and gave them a few simple helper functions. Now, we also did this thing where we abstracted over the date range. And the idea here is that abstracting over date range lets you calculate the historical value of these features as well as the current value of these features. And this is important because, as I mentioned, the training data set needs to go over much larger data volumes. So we want to be able to break this up and chunk it up and do all the nice things that you want to do with this. But the problem is that it's actually really tedious and complex to define features in this way for most users. A lot of the systems that they were getting their features from, they already had some SQL queries, for example, that would they wanted to basically just paste in and have this stuff all happen automatically. And another issue that we found was that duplication of code and the correct abstraction of code was starting to become a real problem. And the reason for this is that with Spark, you need to know which tables are being read from. You need to know how data is moving through your system. You need to know where I/O is happening. And you need to try and consolidate these things to avoid all of these expensive components within the system. And because each one of these features is defined independently of one another, you end up basically having to know about the implementation details of every other feature to know how you can best optimize the system, which is obviously a very challenging thing to do. So ultimately, the performance of this system degraded really quickly when we started letting more and more users use it. On top of this, it became quite obvious that users really, really wanted the SQL option, or they wanted to be able to sort of interact at a higher declarative level. And you can imagine something like this is actually really hard to optimize at a domain level because we then have to go and start parsing SQL strings and so on and mapping that back to the actual things that they're reading from. And so on top of that, testing is an absolute nightmare. So we went back to the drawing board and we said, this is all just way too complex to use. There are too many ways that users can make mistakes, and we don't want that. We want to make the experience nice and simple for them. And so what we did is we took some inspiration from the Sparks and the TensorFlows and the functional programming communities and basically said, let's think about making a higher level declarative language. And so Spark has this thing called the catalyst optimizer, which takes your DAG, which is the description that you build up of the program, and then basically optimizes it and rewrites it for you to make it run faster. So we thought maybe we could do the same thing, but at a higher level, at the domain level. And the idea here is that we can take these feature descriptions potentially and then globally optimize that set of features that are going to be run into efficient Spark code. And so we ended up doing exactly that, and it looked like this. So we'd have feature 1 as declared in Scala at this particular point, and then feature 2, feature 3. We would take it into our feature engine and spit out these optimized features. Now the output of these features would become the input to Spark. So the nice thing about this is that we could centralize our logic and we could improve the performance transparently to users, because all they were really interacting with were these bits on the side, the blue, yellow, and red parts. And so our feature generator would be that abstraction layer. We kept improving this, making things faster and faster by writing more and more efficient versions of the code. And this was a really nice property to have. So as sort of to visualize what this might look like, the output might be an optimized transformer that rather than spitting out a single column like we saw before, actually spits out 3 columns in one go. So you can imagine if we start combining all of these things, we actually get more and more features written in one go. That means a lot less I/O, which happens between every one of these joins. And so ultimately, most optimization techniques that we applied were about reducing I/O, sharing compute, and sharing caching where possible. So some examples were exposing interfaces to make smart use of the HDFS partitions and avoid reading too much data. So you don't want to read a 100 terabyte table 10 times if you can just read it once, for example. We did things like combining multiple features that read from the single table into a single read, and we did things like caching common aggregates. So if you had multiple tables that did some kind of group by or join beforehand, and then a whole bunch of features were defined off of that, we would then obviously cache that table to avoid needing to recreate that intermediate cache. And Spark can do this if you write everything efficiently from the get-go, but because these were all independently declared, we needed to actually write this for the users on their behalf. And the whole idea here is that we avoid the users having to worry about these implementation details of Spark. So as an example, you can think of the absolute simplest feature, which would just be selecting a column from another table that already has the feature logic defined, for example. And so this might look something like the following. You've got your optimized transformer on the bottom left, and that just takes in that first feature and appends the first column. And then the next transformer would take in that first column, and then it would have to do a join. But you can see already that this is a really inefficient way to do this thing, right? Because realistically, you could rewrite it like this. And this is basically combining that select from the first one and the select from the second one into a single pass of that table. And so our feature generator would spit out this optimized feature that would basically just spit out both columns. So we went from the kind of code that looked something like this, where users were having to worry about these date ranges and all these different problems, and it became a lot more declarative in nature. So basically what was happening is that we would have, say, a column feature as the simplest abstraction, and we were able to select out just a specific column from it. And then we would have, say, the table, we'd have a few different defined tables, and we'd have efficient partitioning strategies for the different types of tables so that we could actually read these things very quickly. And then all we did was enforce that certain metadata existed. And then on top of this, we exposed some slightly more complex logic, such as like windowing event features, doing counts, as I mentioned before. You might think of one of the features as how many times has a user visited this page in the last 30 days. This allows them to literally just say, I want this event out of my event store, and I want to window it over the last 30 days, 60 days, 90 days to get sort of the historical trends. But this is all still Scala, right? I mentioned that our users were mostly Python users. So on top of this, we said we could probably abstract this even more and make it even simpler. And so what we did was move this into a UI. And the idea here is that you can use the interfaces that we defined to create these different types of features. And on top of this, because it's all defined centrally, we can now do things that are really tough to do if it's just a code base, such as feature discovery, feature metadata, feature management. And on top of this, we could start doing some really useful testing. So we were testing the interfaces extensively. So we knew that they were actually doing what they said they'd do. And then users could confirm that their implementation was working correctly by looking in, by running their features in a dev environment, for example, and comparing it against what they expected. And then on top of that, we were able to then define features for particular projects. So I mentioned earlier that you have the training phase taking in a set of features. You do some learning to work out which ones you actually want, and then that becomes your scoring set. So those were very easy to define at that point through the UI. And then we said, okay, let's open this up to some more users and more features. And what happened is that our cluster got absolutely annihilated. And the reason for this is because we failed to ask ourselves one big question. And that question was, who pays for this thing? And it turns out that if you don't have a good answer to this question, nobody pays for it. And you end up basically just trying to scale with what you've got. And that's never going to work. So we were very unfortunate in this, and I really encourage you, if you're going down this path or have gone down this path, to really think about the right way to do this. But for example, if you've got a question of, will the feature store get a budget of its own? You need to start thinking about how you actually plan for the capacity of this feature store, and knowing how you're going to have some kind of fair use policy if you are giving it a fixed budget, for example. And this is going to differ from organization to organization. Or you can look at something like, do the projects actually pay for their usage? And if they're paying for their own usage, what are they paying for? As I mentioned, we're taking all these things and smushing them into one big efficient job. Trying to untangle which bits of compute were actually associated with which features is really challenging. So we came up with a solution to this, which I'll get into a bit after. But ultimately, this cost question led us to rethink the entire idea of whether we should be centralizing a feature store at all. And so we did a little bit of investigation and noticed the following problem. So project 1 would come along, and they'd say, okay, we want features 1 and features 2, and we want it for time 0 and 1, and we want customers 0 and 1. And then project 2 would come along, and they'd say, well, we also want feature 1, and we also want feature 3, and we want a sort of similar customer base, but they're actually not completely overlapping, and we actually want to train it on this particular time range. And so what ends up happening when you explode this out into its tabular form is that you end up with a ton of data here that's either not used or it's not defined. And the reason that this happens is that you've got these non-overlapping customer sets. So the various source systems that you get the feature declarations from may not even have the data that you need to define these features. And so obviously this was a huge problem. We're doing a lot of work that we don't need to be doing. So we said, okay, let's start thinking about some optimization that we can do to this whole process. And so we looked into the actual usage patterns and noticed out of the 30 million customers defined across all systems, which amusingly is significantly more than the total number of people in the entire country, we had customer set 1 in source system A and customer set 2 in source system B. And each one of them would say generate the blue types of features or the red types of features respectively. So what that means is that if you've got, say, an overlap of 10 million and you want to use, you want to do some modeling where you use features from both of those source systems, you kind of need to use this bit in the middle. And so what we looked into as well is what are the projects specifically using, not just what do people want to be generally having available. And it turned out that they were doing something like this. They would, for example, being a telco, they might look at postpaid customer churn for their mobile services. And so that would target a very specific group of customers within one of their source systems. And this might be, say, 2.5 million customers. And then if you think about the set of customers that they can actually then do some meaningful training on, it's even smaller again, which ended up being, say, 2 million of the total 30 million. Now, this is obviously a huge difference in scale. So we did some quick back-of-the-envelope calculations, and you can kind of realize what's going wrong here with what we initially tried to do. If we have, say, 30 million users, we have 365 days of data to generate. We've got 2 years, say, and we've got, say, 1,000 features. And the reason we have 1,000 features is that every project comes along and says, oh, I want 300, I want 200, I want these 150. Some of them overlap, some of them don't. But if we're trying to keep all of them in this big central table, we get this big problem where it explodes out massively to, say, 22 trillion data points. But what every project actually needed was closer to 500 million. And the reason for this is that we've got a much smaller customer base, and we've got a lot less features that each particular project needs. So we thought about the existing headaches. So generating all of the features for all tables across all the time is an enormous data challenge. 22 trillion values for the cluster size that we had was pretty considerable. Probably not for Google scale, of course, but yeah. So then, ultimately the problem here is that you're doing way more work than is necessary, right? Most of the projects aren't actually using this kind of data. And you're always increasing your compute burden as you add new features in history. And just on that previous point as well, very often the good advice is to have as much data as you possibly can. But we were finding that most projects that got all the data they requested were really struggling to actually scale their training algorithms. So it actually was even worse. The problem of getting to market quickly was multiplied by doing these bigger and bigger data sets. So on top of this, if you're using HDFS, trying to keep these things highly available while adding new data to it and so on and so forth is actually quite a challenge. And ultimately, you end up needing to do things like copying the data and keeping it immutable, which is a great pattern, but at the scales that we have is actually a huge problem. It takes a long time. So we had this crazy idea. Maybe instead of having this big central thing where it seems like everything is available and easily grabbable, what if we just generate the training data when people need it? Because we have these much smaller data sets that people are actually using in practice. This would remove an enormous overhead. It would, like, the engineering cost of maintaining this central table is huge. In particular, we were using older versions of Spark, which were just the most buggy thing you can imagine. I hear a few people that probably feel the same. So what this meant is that we could get teams to start modeling a lot quicker. And the reason that we could do this is because we were generating a lot less data. So if someone comes along and says, hey, I'm going to sample my customer base and I'm going to look at the last 3 months of history, they could cut down the amount of data that they needed considerably. So instead of us having to append this to this massive table and have a whole bunch of data that has to be generated for it to append properly, we could just generate what they needed. And ultimately, because we were doing this generation every time, the thing that we spat out was in the perfect format for them to do their machine learning on. So for better or worse, we explored this approach and decided that we need to make snapshot generation as fast as possible. And so we looked into some of the things that were actually the bottlenecks in our system and found two kind of key things. And the first one was the DAG. So we look at the Spark DAG. You can, if you recall, we have these feature transformers. So they're taking in some data frame, they're doing a join with the features, and then every time we take in the next one, say, and we join 2 more features on. And what ends up happening with the Spark DAG is it looks like this. And if you can probably spot the problem, we've got this linear sequence of joins that needs to happen, right? And the problem with this is that the first join needs to complete entirely before the next one starts. We have a dependency relation between them. But really, we don't care what order they join in so long as they all end up in the last table, right? So this was a huge performance bottleneck because this also represents the I/O in Spark. And so what we did is we said, how about we push some of these features up to the leaves in a tree? And we said, okay, let's generate each one of these optimized sets of features independently. We'll join each one of them logarithmically and end up with that final table. And what we had to do to make this happen is instead of using a big left join where we started with all of the customers and all of the dates, we said we'll just do whatever each one of these leaves care about, and then that will naturally fall down with full outer joins. And so the DAG ends up looking something more like this. And the nice thing about this kind of DAG is that you can throw more and more executors at it and it will continue to get faster and faster until a specific point. And that specific point tended to happen very much towards the bottom of this DAG. And so what we actually found, if we were to compare the old approach versus the new approach, is that the old approach is this blue line, right? And so it would shoot up to 100% utilization very quickly. It would be calculating the features for a little while, but then it would very quickly end up in this linear join that would take a really long time. With the new approach, though, we found that the executor were being utilized a lot more of the time, and this meant that we could throw more and more executors at it, and it would become faster and faster until you get that similar kind of peak look. Now, some other thing, we did a whole bunch of other optimizations, as you can imagine, but another one of the key ones that we noticed is actually a really simple one, but it's got very big consequences. So with parallel processing, you can imagine if you've got 30 tasks that you want to process, each task takes time t, and you've got 15 resources to process this thing. You do the first 15 in time t alone, and then you do the next 15 in time t as well. So the entire thing takes 2t. If you have 200 things to process, and you do the first 196 of them in time t, those last 4 also still take time t. And when you look at these things visually in Sparks UI in particular, this is a little bit counterintuitive, but you're actually taking the same amount of time to do this, even though there's only 1 or 2 tasks that are dangling at the end here. And so you need to either drop the number of tasks that you want to be parallelizing or increase the number of executors such that you can run this in a single pass. And that will literally halve the amount of time. And so for us, because we were doing, pushing all of these computations into these stages, what ended up happening is this T was really big. And when we're doing something like this multiple times and each one of these T's are double what they really need to be, this is a huge overhead. So this tiny little optimization actually more than doubled the time it took for our jobs to run. Sorry, halved the time. And so finally we looked at the Spark version that we were using, and we were lucky enough to convince the right people to actually upgrade the platform. And if you're stuck on 1.6 still, or if you're looking to get in, please do not use 1.6. Performance in 2.x is astronomically better. We benchmarked it on some of our use cases and found it to be up to 17 times faster. It's still obviously not necessarily the fastest thing out there, but in terms of simplicity, it's really nice. And on top of that, one of the biggest pain points that we felt prior to the upgrade was actually stability. We would do stuff that seemed as simple as just taking some data and writing it to a file, and it would crash for a million different reasons that just seemed completely unrelated to what we were trying to do. And 2.x fixed a lot of these problems, so definitely check it out if you haven't already. So in terms of the actual relative performance gains, don't worry too much about the actual number of hours. This is a function of our compute and the types of features that we're generating. And as you can imagine, types of features are a pretty bad thing to be benchmarking on because, as I said, it could be as simple as just selecting a column from another table or even just generating some data. Or it could be as complex as looking over the last 10 years worth of data and doing some complex aggregation across these things. What we found is that with the standard approach, we were taking, say, twice as much time as a declarative approach, even for the simple, tiny little generators. But for the declarative and optimized approach, it was so much faster that it was basically negligible. It was taking something like 15 minutes to generate 3 months of history for, say, 50 features, which isn't what you want to be training your final models on most likely, but it's a really great starting point. You can get that in 15 minutes, see if you've got any kind of meaningful correlations and do some of your feature selection and all this kind of stuff before moving on to the bigger and bigger data sets. And more importantly, you can see in the rightmost column in each one of these things, the first 2 would never actually finish on the big feature generation jobs. They would either crash, run out of memory, we wouldn't be able to get enough compute, or they would literally just never finish. I say never because we never let them run long enough. We let one of them run about 4 or 5 days and it didn't finish, so we very much gave up. And now what this meant is that we now have the ability to go from the very beginning of a project, declaring your features in a UI, and having an actual snapshot of data that you can use for a big data training set. And this is normally something that takes weeks to months at a lot of enterprises that aren't mature with this kind of stuff. So finally, once we've trained these models, I haven't spoken too much about the actual training of the models in terms of how you scale this, because there are a lot of things out on the market now that do a really good job of this. In particular, AutoML is becoming more and more popular, and it's able to automate a lot of the different training strategies that you might want. So it can do all these various grid searches and stuff, and find the best set of hyperparameters and so on and so forth. But finally, model serving is, as I mentioned, where you take that model that you're happy with, and you want to put it in production, and you want to start making predictions with it. And it looks, again, something like this. You're going to need your features. Those set of features, they're going to have to generate in production. And then you also want the final model that is taken out of the data science process. And there are kind of two primary ways that you can do this, and that is sort of conceptually a data to model scoring approach where you send your data to your models. And this is very common in the sort of containerized world with Kubernetes and so on and so forth. And then the other approach is kind of the big data approach, I guess, where you want to be doing massive scoring runs where you might score your entire customer set. And this is kind of more your Spark worlds and your Flink worlds and all this kind of stuff. And so the idea here is that you send your data to the place, your models to the place that the data actually sits to avoid all of that expensive I/O. And so the way that our feature descriptions and feature generator were able to slot in is that because they were just descriptions, we could pass them around. We didn't have to do anything special here. And ultimately, they can just sit in between the data sources and whatever you care about at scoring time. Now, because we were using Spark and so on, we used the right-hand side of this with the model to data deployment. But we still have some problems, right? Because different projects have different requirements on the type of scoring they want to do. So for example, the feature values might update at different rates. You might have a data source that historically you can obviously get all the data for, but right now it's actually 3 days delayed and all of your other data sources are up to date. So some projects might care about this and they might say, well, okay, I just want the most recent data that I can get for all of them. And they might have done some clever stuff in their modeling to compensate for this. Another approach might be to say, well, I only want the most recent consistent snapshot as of a particular date. And so other people might want to only materialize the bits that are up to a certain point in time. And finally, other projects might actually have as part of their feature pre-processing the idea of imputation. And this basically means taking a guess as to what data you want in here. And there are various different strategies for this, but if the feature that you're imputing is important, this can actually be quite problematic. But ultimately what we ended up saying is, okay, let's treat everything using the Kappa architecture. We're going to treat everything as a stream. We're going to pass it through Kafka. And because we have these declarative features, we can run them on both the batch and the streaming sources just by implementing a slightly different optimization on the back end. And that would spit everything out onto this Kafka topic as EAVT. And what this meant is that we could then materialize it in whatever format we cared about. So for the projects that wanted it as a big batch, we would materialize it into Hive, say. And if they wanted it just as the most recent value at a particular point in time, we could do it into HBase, and they could do selects as of particular dates and stuff. And then we also would allow, obviously, people to connect directly to Kafka and start doing Kafka streaming things for the more specific and particular use cases. And ultimately, all of these would feed into the model scoring process. And some people, even with the Kafka option, would use these for various other options. So there was an example, someone calls up the call center, and we want to be able to score a model very quickly and basically give a recommendation as to what to talk to them about. So ultimately, there are a few key takeaways, I think. The first is that naive centralization, and I stress the naive, is very hard and very expensive. It really pays to work out the real usage cases, not just the desired usage cases, because big data is, as I said, way more complex than it really should be, but it just is. So if you can cut down your problem to be a less big problem, then you're actually dealing with much simpler problems. And working out how to manage resources and cost early on is really important. So as I said, we kind of went down the path and then realized about halfway that this wasn't something the business had been on board with in terms of how it was going to be funded. You really, really, really need to do that early on. Additionally, a lot of you are probably thinking, there are so many different ways that you can write features. How on earth could you possibly write interfaces to cover all of these? And the reality is you don't usually need to. So a lot of businesses work in fairly constrained domains. They have a limited set of data sources. So we went for the 80-20 rule, and we said, let's define the types of computations on the types of data sources that people are using, and we'll hyper-optimize these things. We'll make these things really efficient to do. And then we'll expose the underlying transformer interfaces for anyone that needs to do anything more specific than that. So this means that, say it was taking a couple of weeks to define all of your features previously, you could get most of that done in one day. and then you just spend a couple of days, say, doing the really specific stuff to your project. And this is a huge win for the business because it means that you can get to market a lot quicker. Now, another key part to this entire design and this entire process is that features need to be independently declarable. The biggest problem with having features not independently declarable is that you have to worry about implementation and you have to worry about how they all relate to one another. And this is not what you ideally want to be doing. Because on top of this, the more declarative you make this interaction, the more you can actually do for your users transparently. You can take, as we did, for example, take these features, smash them together, and basically write a compiler to make it more efficient on the execution side of things. So that's about all I've got today. Thank you very much, and hope you've enjoyed it.
Any questions? It's pretty intense. People are still digesting stuff.
So two questions. The one would be, thinking about changing the framework completely. There's like data flow / Beam, etc. So one question would be, was that a consideration for you guys?
So we were on-prem. There was no plans for this particular company to migrate to the cloud when I was there. Things like Beam, I don't think would have added that much value on top of Spark, to be honest, at the time. I think certainly if we had something like GCP as an option and we wanted to use Dataflow, that would have been very, very nice. But that would also be a really nice way as well, potentially, to abstract over the implementation of this thing. So yeah, absolutely. If that's something that is important to the company, then that would be a great option.
Yeah, because it's something saying the Google guy has to mention a little bit, but I think some of the challenges, right? And suddenly you have a certain set of data and doing this on premise, and if they always have there, right? Getting the hardware, getting provisioning, those are the classic kind of drivers to hey, if you can do this on demand,
exactly,
right? It makes that pain go away. And then what I really like in your talk is that it's interesting to see, Sad, that making some of the base constraints go away makes you sort of unravel and rethink the complete architecture, right? Somehow people had an assumption that getting the data set was difficult to do. So they made a decision that, build a thing that has everything.
Yeah.
But once you solve that constraint of it's no longer that difficult to make a data set, it really simplifies your architecture. I think that process is one that really I just want to put back in people's heads, right? Often you have these presupposed assumptions that, a centralized thing that does everything is good. Right, but it's only good if you're living with certain constraints, and if you make those constraints go away, it really broadens the option. I think this is a very nice example of that.
Yeah, thank you. Yeah.
So, hopefully that broke the ice for questions.
Hi, sure. Sorry.
Sorry, I did miss part of what you're doing, so I might be asking a question specifically about something you answered, but the you were talking about historical data and current and the event flows and everything else, but sometimes we want to. I work at Standard Chartered, and we're trying to use machine learning for signature comparisons and those things. Mm-hmm. And so often we're saying it's a real-time event that we want to throw into the pile and get a response out instantaneously.
Yep.
And the model that we need to apply against it is one that was pre-computed some time ago, and those kind of sessions. Have you, in this type of setup of distributing that workout, have you dealt with anything in that kind of space?
Yeah. So that's actually, it sounds like you're saying you've got some offline process that actually trains the model, and then you want to score it in real time by basically spitting stuff through. And that's actually, on this slide, exactly what this is doing, right? You've got, say, a Kafka topic coming through here, and you want to calculate whatever features need to go into that model, spit it onto the topic, and then they ultimately go straight into your model as the inputs, and then you just get a stream of predictions if that's the kind of thing you're doing.
Sorry, I wanted to pass the model in as well, because I wanted lots of models.
Yeah. So the models are downstream of this whole system, so you can have as many models as you want. And basically so I didn't really talk that much about it, but we actually had kind of a mini framework internally that you could just submit a model to, and it would basically deploy it at the end of this pipeline for you. And this would basically just automate that whole process.
That was what I wanted. Thank you.
Yeah.
Yeah, so in this type of setup, like, was there any need of doing model versioning? Because, like, people run experiment, look at result, and then iterate over that.
Yeah, absolutely. So obviously there's the model versioning on training, and then there's the model versioning on what we're actually deploying. So if you're kind of going down this path, and you've kind of on the left-hand side with the Kubernetes, you can put your models in, say, a Docker container, and then that can be your unit of deployment, and you can kind of version models that way. There's a lot of different approaches to this. HDFS, it seems like the general approach people use is to actually just save the serialized models on the file system. I'm not really a big fan of that, but that's another potential option. We actually used, I think it was Artifactory, so we basically just published them as artifacts and then pulled them down, very similar to kind of what you'd do with if it was managed through Docker. And then we'd pull that down and pull out the specific ones that people were asking to score.
Could you elaborate a little bit on the differences of data to model scoring versus model to data?
Yeah. So the main point here is that one of them, you're sending your data over the network to be scored, and the other one, you're basically sending your models to the data such that it scores locally. So depending on the type, generally it's the volume of data you're trying to score at a time. So the one on the left is usually if you say running a website and you want to do a quick score of a particular customer or something like that, whereas on the right it might be if we want to predict churn across all of our customers, we want to do that in one big batch job, and we do that maybe once a week. So you want to, instead of sending all that data over the network, which is really slow and expensive, you send your models to the actual data such that it runs locally and is done a lot quicker. And this is where things like Spark that distribute assets and all that kind of stuff works really nicely.
But if you're sending the model, you don't train it, right? You just score.
Yes, yeah, this is all for scoring, yeah.
Oh, okay.
Yeah. So training is a completely separate step.
Okay, thank you.
No worries.
Awesome. Thank you, everyone. It's 4:25 now. We head out for a break and be back here from 4:45. Thank you, Cameron.
Thank you.